Good morning, or whatever. It's time to learn a little bit about simple harmonic motion, which we abbreviate as SHM. Simple harmonic motion is a very important mathematical model, and it's important because a lot of different types of motion can be considered or approximated as simple harmonic motion. This is where in physics we kind of make things up. Simple harmonic motion, the mathematics for it are very nice once you kind of get used to them. And other things have mathematics that would be not so nice. So we just pretend, in many cases, like the object, even when it's not quite, is moving in simple harmonic motion. And that makes our lives easier. Many times what's actually happening is that it's moving in maybe harmonic motion. Harmonic motion is less simple than simple harmonic motion. We'll talk about it a little bit briefly, maybe at the end of this lecture or in the beginning of the second shorter video. But for the most part, we'll stick with simple harmonic motion. The simplest case of that would be a spring mass system, which I'll show you here. So we've got this spring oscillating up and down, and this is undergoing simple harmonic motion, almost precisely, especially if it's a simulation-based spring mass system. In the real world, it wouldn't oscillate between the same points. It would start to what we call damp out, and then it would no longer be simple harmonic motion. But as long as it doesn't happen too quickly that it diminishes its amplitude, we would still approximate it as simple harmonic motion. Some other things that would undergo simple harmonic motion or approximately would be pendulums and things like electrons and molecules and stuff like that. When they oscillate, they undergo approximately simple harmonic motion. So you might be thinking, yep, I get this whole idea that the mass is oscillating up and down, and you can probably see that it slows down towards the bottom and it slows down again towards the top and speeds up kind of in the middle. Whoops. Okay. So speeds up in the middle, those types of things. But what is going on with this phase space over here? And why is this little green dot just going in a nice little circle? Well, this green dot is moving in uniform circular motion, the mathematics of which we already know. And if you look carefully, you should be able to see that the green dot, its vertical position, is lining up at all times with the vertical position of the spring mass system. And this is the beauty of simple harmonic motion. We take a motion that in some cases will be fairly simple, like that of a spring moving in a straight line, or in other cases a little bit more complex, like a pendulum swinging back and forth, and we basically map it onto a uniform circular path with an object moving in uniform circular motion. So what I'm going to do next is I'm just going to go through and basically take you through the mathematics of how this works out, and how we can take the motions here and project it back onto the motion of the spring. Alright, the first thing that I'm going to do is just kind of define the geometry of the situation for this spring mass system. And here I have this nice beautiful straight line that goes from the bottommost point here. So if our little green dot was no longer green but black and was down at the bottom here, if I just project that over off to the side, this would be the lowest point that the spring mass system gets to. Its center of mass would go down to this point. I'm going to define that as a position of negative A, where A stands for the amplitude of the oscillation. Now if the green dot were over here, corresponding with the center of the circle, that would mean that my nice perfectly straight line would take me over to somewhere around here, and this would be what we would call the equilibrium position, so y equals 0 there. And likewise, if it were at the top, we could map that over and we would get something around here, and this would be y equals a. So the distance between these two and these two should be about the same. They should be a and negative a. So that's the first part. If this was not simple harmonic motion, if it was damped harmonic motion, then this amplitude would be constantly changing, and this green thing would have to be actually going in a spiral, which would be less pleasant to deal with than going in a nice uniform circle. So what I'm going to do now is I'm going to focus a little bit more on this little green guy here and how that makes sense with the spring mass system oscillating up and down. So let's go with something green, and if I just mark a handful of points here. Okay, so I've got this here, and it's moving in a nice, actually let's do it this way. So it's moving in this nice straight line, right? It's got this velocity, And I'm doing not a great job of drawing the line. This one should be a little bit more horizontal. And this one will make straight down. And all of these have the same magnitude, okay? But let's say that we're just off to the side, and we're looking at this, okay, with just one eye. Maybe we've closed the other eye, and so we're just looking at the scene off to the side, viewing the scene over here. And by closing the one eye, we don't notice the depth. So we're only noticing the motion sort of across our field of vision. And from our eye's perspective, then, we only notice, in essence, the vertical component. And I've just realized, can you see the eye that I drew? No, you can't. You can't see the eye that I drew. So here's the eye. This is how we draw eyes in physics, by the way. It's very sophisticated. And so what I'm doing is, if this eye was actually like way over here, off to the side, far away, and we only had the one eye viewing it, we would only notice the vertical components of the motions. So we have Vy here would just equal the overall velocity, because it's completely moving across our field of vision. If I look down here, Vy, that should be V, Vy would equal 0, because it's not moving at all across our field of vision. And if we look at any point in between, we're going to get some component that's vertical, and as we get closer to the bottom, that component that's vertical gets less and less and less. And so it turns out that we could actually describe this if I define an angle. Let's call this angle here, I don't know, theta. So we'll call this angle theta. What we could do is we could actually describe the vertical component of the velocity as v naught sine, as v naught sine theta. And if I want to be very particular, in this case it would be negative v naught sine theta, because it's going down. So this would also be negative, and so on. But that's the basic premise. We could actually then, if we go back, this would have an angle of 0, let's say. And so when we, I'm sorry, does that make sense? I guess that's how it'll have to work out. This is going to have an angle of 90 degrees, actually. So this would have an angle of 90 degrees, which is why if we do the sine of 90 degrees, we would get the maximum amount. And down here, if I did v naught sine theta, where theta equals 180 degrees, also known as pi, we would find that we get 0. So that's how the velocities work out. And we can also play a similar game with the positions. So if I just look at the green dot when it's up here, and it's slightly this putrid off-green yellowish color, let's try again. Let's do something a little bit fun. Red. We'll go with red. So I've got this red-green dot, and it is a particular distance a away from the center of the circle, so that's also r, and that matches up with our maximum amplitude here. And because it's moving in this direction, what I'm going to do is I'm going to split it up into thirds, approximately thirds. Okay, so this will be theta. So I'm going to measure theta always from this point, which is how I got this to be 90 degrees and this to be 180 degrees. And so this would be 30 and 60, and then we'd have 90 degrees down to there. And what I want to do is I want to define the position at each of these points. So this would correspond to y equals a. That's an a. This would correspond to y equals something not quite a, but it would actually be a times the cosine of theta. Because if we go back up here, if I have a times the cosine of 0, I would just get a. And as we get further down, and we continue to define this as y equals a times the cosine of theta, we notice that it gets smaller and smaller until we get to this point right here, where we would have y equals a cosine theta. But when we do the cosine of 90 degrees, we just get 0. So by this sort of simple construct that the position would be equal to the amplitude, the maximum amplitude times the cosine of the angle, and v would be equal to the, you could say, the maximum velocity times the sine of the angle, we can actually describe a lot of what's going on. What might not be quite so obvious is what happens with the acceleration. But if you think about what's going to take place, down at the bottom we actually have the vertical component changing quite rapidly. If we're looking at it sort of in the middle regions, as it starts to angle over some, that increase in the side to side that happens is not countered by an equal amount of decrease in the vertical. It's that whole a squared plus b squared equals c squared aspect. So we actually tend to get less acceleration in this range and more acceleration down here. And hopefully I can explain that with forces, but I'm going to do that in the next video lecture because this one's getting a little bit long. So that's it for now. Take a little break and then we'll reconvene and talk about acceleration, and then hopefully talk about some of the principles behind these equations here.